And yeah, so most days I'll start with a question for you guys to work on, so that we're not just watching and doing something fun to start with. And so if you want a little extra time, you can show up early, and you'll have like an extra 10 minutes, I guess, to work on the warm up problem. So we're doing the 2 day forecast. Let's see what you guys said. Is there a consensus in the class? So it looks like 7 people think it's this one. 5 people think it's this one. 2 people think it's this one. Let's see what it is. And I think for the 2 day forecast problem, it's not too bad because you can write down all the possibilities. So we're doing the 2 day forecast problem. If x0 equals rainy, then probability that x2 equals rainy equals question mark. That's the question. And we're only looking at x2, so we're looking at sequences which go rainy, sunny, rainy, sunny. That's what the Markov chain is, right? It's a sequence of these outcomes of rainy or sunny. And they're only length 2, so there's not that many. They start with an R. They got to end with an R. There's really not that many. Let's write them down. So could be, what could it be? Could be, it could go rainy, 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 right? And so here I'm writing down the sequences. So it could be, when I say could be, I mean, what is x0, x1, x2? It could be rainy, rainy, rainy. That ends with a rainy, starts with a rainy. That's what it could be. Or it could be rainy, sunny, rainy. And because we're talking about starting with rainy and we're talking about ending with rainy, those are the only 2 possibilities. It's really not so bad. And each of these things, we can calculate the probability. There are disjoint events. We can add the probabilities at the end. So let's see, what is the probability of rainy, rainy, rainy? Well, to go from rainy to rainy on the first day, that's an alpha. To go from rainy to rainy on the second day, that's a probability alpha. What happens on the second day is independent of the first day. So in a Markov chain, what happens on the second day isn't impacted on what happened on from day 0 to 1. So the probability of this guy is alpha squared. Probability is alpha squared. What about on this rainy, sunny, rainy sequence of events? Well, rainy to sunny is not an alpha. Rainy to sunny is a 1 minus alpha. And sunny to rainy is the other rule in the Markov chain. That is the beta. And just like before, you can multiply them. So the probability for this guy, the probability is 1 minus alpha beta. And we're talking about this thing happening or the other thing happening. If you add them up, you get alpha squared. So the total probability. And the total probability is the probability that we end with rainy. These are all the possible ways you could end with rainy. Alpha squared plus 1 minus alpha beta. So I think that was the option that 5 people picked. Let's see. Alpha squared plus 1 minus alpha beta. So 5 out of 14 people got it right. A lot of people went for this one. This one looks nice and symmetric. But there is like kind of an asymmetry, right? Because rainy, 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 and rainy, sunny, rainy. You always have 2 rainies out of 3. You start and end with a rainy. Any questions or comments about that one? Maybe somebody in the chat is saying alpha was the other way. Yeah. So I think I had a typo in this at one point. Maybe that screwed you guys up. But I believe this is the one from the notes and from the textbook we're following. The model is like this. Okay. Yeah. So yeah, my bad if if you guys got screwed up because something was wrong in the question. Any questions or comments about that one, or anything else with this Markov chain? Okay. So yeah, sorry guys if something got screwed up here. All right. Yeah, I believe the order of the answers is random for everybody. Maybe that's part of the confusion. But that's the 2 day forecast. So let's work on the 7 day. The 7 day forecast. Okay. So we did the 2 day forecast, and for the 2 day forecast, you could write them out. For the 7 day forecast, if you want to write them all out, I mean, you could do it. You're going to be here for a long time. That's because we're going to have sequences of length 7, or I guess 7 that start with an R, and there really are like a huge number of these sequences. So for the 2 day forecast, it's no problem. You can write it out. But for the 7 day forecast, we would rather not write it out. So you could write it out. Write out. How many sequences would there be? There would be something like 2 to the power 7 sequences. I guess there's 2 to the power 7 sequences that start with R. You want all the ones that end with R. So maybe there's only 2 to the power 6 sequences, which is too many. So what we want to do is we want to find a different way to do this problem, especially because we want to figure out a way to do this in a way that gels with how computers work. We want to be able to put this on a computer, and having the computer calculate like these exponentially growing number of sequences is just getting like bad for the computer. So we kind of want to keep things away from exponential and do it in a smarter way. So what we are going to do is, instead of looking at all the possible ways to go from day 0 to day 7, we are going to kind of go sequentially and think of how is the probability of being rainy updating day by day. We did it for 2 days already, and we can store the answers in a vector that is updating. So I'm going to define a probability vector, which has the probabilities, the information we want. So I'm going to define v for vector sub n. Let's do v0. V0 is going to be 1, 0. And it's a row vector where the first entry is the probability it's rainy. This is the probability x0 is rainy. And the second entry is the probability that x0 is sunny. So it's a row vector that stores these probabilities. And v1 is the probability on day 1. So the probability x1 is rainy, and the probability that x1 is sunny. Okay, and this one is alpha and 1 minus alpha. V2 is what we just did. V2. So V2, has a funny combination. So it's alpha squared plus 1 minus alpha times beta. I guess the other term will be 1 minus all that. And so instead of trying to do all the possible ways to get from the start to the finish, we're just going to think of updating, going from Vn to Vn plus 1, where Vn is this vector, the probability that Xn is rainy, and the probability that Xn is sunny. And we're going to see if maybe there's a nice update rule. And we're just going to exactly do what we just did to figure out the 2-day forecast. We're just going to repeat that, thinking of going from day n to day n plus 1. So how do you get the probability that xn plus 1 is rainy in terms of, so we want this in terms of the probability that xn is rainy. So something involving that. I'm having a little technical issue. Let me reopen this. Did that fix it? Okay, there we go. Okay, so we're just going to update one by one. Yeah, Alex has a question. Go ahead, Alex.
Yeah, just before you start really getting into this, can you just briefly explain what an update rule is?
Yeah, so by an update rule, I just mean we're going to take the information from vector Vn, and we're going to try to update it to get Vn plus 1. And so the idea is, it's not like a mathematical definition. What is an update rule? It's just saying, instead of going from 0 to 7 and like trying to do it all in one shot, we're going to update little by little. So instead of going from day 0 to day 7, we're going to go from day 0 to day 1 to day 2, day 2 to day 3, all the way up to 7. And hopefully the rule for going up 1 day is easier than the rule for going up 7 days, and we'll just do it 7 times.
Okay, sweet. Thank you.
Yeah. And so we're gonna see that there's actually a really simple rule. So yeah, I guess once we know what the rule is, then you'll know what the update rule is. Okay. So that's the idea, that instead of trying to do 0 to 7 all in one shot, we're gonna just focus on doing one step at a time. And if we can write that really nicely, maybe we'll have a shot of getting all 7 days. Yeah, sorry, my camera's not focusing right. Let me try to fix it. Okay, I guess you guys are gonna just have to live with a blurry face. Hopefully the math is not blurry. Okay, so what is the rule? It's essentially what we just did for the 2-day forecast. So if you understood the 2-day forecast, I think you will understand what's going on here. And it really uses the law of total probability, or just thinking of all the possible ways you could get to a rainy state from a non-rainy state. So I'm going to write it out like this, and then we will update it. How could it possibly be rainy on day n plus 1? Well, there's 2 possible things that could have happened on day n, right? It could have been rainy on day n, or it could have been sunny on day n. And in either of those two cases, on the next day, there is a certain chance that it becomes rainy on day n plus 1. And the chance is this conditional probability. So that times the probability that xn plus 1 equals rainy given xn equals rainy, plus the probability that xn plus 1 is rainy given xn equals sunny. So sort of if you know the two probabilities that it's rainy and sunny on day n, you can combine them with this linear combination by the law of total probability to get the probability that it's rainy on day n plus 1. And we're not missing any cases here. It's either rainy or sunny on day n. So those are the only ways it could happen. These two probabilities, the probability that it's sunny and rainy on day n, those are the information from vector vn. The probability, these conditional probabilities, are exactly what is specified in the Markov chain. This is the probability it goes from rainy to rainy. This is what we've been calling alpha. And this is the probability it goes from sunny to rainy. This is what we're calling beta. So basically, the probabilities on day n plus 1 are a linear combination of the probabilities from day n. And it's the same thing with sunny. It's the same thing with sunny. So the probability, how is it going to be sunny? Well, it can either be rainy or sunny the previous day. And then you multiply by these conditional probabilities. Xn plus 1 is sunny, given Xn is rainy, plus the probability that Xn plus 1 is sunny, given Xn is rainy. And these things, we also know. This one is 1 minus alpha, and this one is 1 minus beta. So the nice thing about probabilities is they update linearly. Okay. So these green things are all information. This is info from the vector Vn, info from Vn. And over here, we update them, like we combine everything in this linear combination to get the information for Vn plus 1. Okay, so we're combining things with linear stuff. You're probably at this point getting some PTSD from your linear algebra class, or hopefully you are. I really think linear algebra is like eating your vegetables of math. Like when you take linear algebra, you have no idea what's the point. The point is this: everything in math basically has linear algebra in it somewhere. It comes up all the time. So this is some crazy big mess, right? That I've written down. But if you write it down with linear algebra, it's actually really nice. So I'm going to write it down, the exact same equation with linear algebra. So this vector of the probabilities to be R and S, that is what we were calling Vn plus 1. On the other side, I have this crazy big linear combination. But linear combinations are just matrix multiplication. And so you can write all this crazy stuff, the sum of 4 terms, each of which is a product of 2 things. It's a linear combination of the vector Vn. So on the other side, I'm going to have sum Vn is a row vector times sum 4 by 4 matrix. So that's what this stuff is going to be. What are the things in the matrix? Okay, let me write it out like this. I'm going to write it out in the long way. So I'm going to say the probability that xn equals r and the probability that xn equals s. That's Vn. Okay. And how am I doing the linear combination? The linear combination is this linear combination. So there's four things because you're doing sums of these two numbers in 2 ways to get these 2 numbers over here. So if your linear algebra is very good, this will be no problem. But I believe it's like this. So I want to do the r given the r. That'll be this times this. Plus, I'll do the probability that xn plus 1 equals s given xn equals r. And then I have the 2 other things over here. Xn plus 1, let me move over a bit. Xn plus 1 equals s given xn equals r. And the probability that xn plus 1 equals s given xn equals this one. I think this one should be s with s. And this should be an r. Let's see if we got it right. So I think this should be an r and this should be an s. Okay, so I've written the exact same thing that we had before, but I am trying to write it down with linear algebra instead of just a big mess. And hopefully that simplifies things a bit. So let's see if it works. So to get the first entry, that's the first row here, we would do this one times this one plus this one times this one. And that should be exactly what we have here. And is it? Well, we have the probability that xn equals r times the probability xn plus 1 equals r given xn equals r, that's this first term, plus the next one is the probability xn equals s times the probability xn plus 1 equals r given xn equals s. So I have it written down, I think, in the right way. And what this is saying, if you replace it with alphas and betas, you have this very nice matrix. Alpha, 1 minus alpha, and beta, 1 minus beta. So even though it seems like a complicated thing, and if you hate linear algebra, it's gonna be a little painful until you get over that hating of linear algebra. But otherwise, the update rule, which seems very complicated, is very simply just matrix multiplication. And we're always multiplying by the same matrix. So it doesn't matter what day you go from to go to the next day. It doesn't matter if it's day 5 or day 6 or whatever day it is. To go from day n to day n plus 1, you always multiply by the same matrix. And that matrix just tells you all the possible ways to go from one thing to the next thing in one day. So this is what I mean by the update rule. The update rule, and it's written very nicely. The update rule is just matrix multiplication. Okay, so the update rule is matrix multiplication. How does that help us solve our problem? We want to do the day 7 update rule. So we want to do the day 7 update rule. So we want V7. So we know V0. V0 is 1, 0. V7 is question mark. And every time we multiply by this matrix. So is there a simple way to write down V7 in terms of the matrix, in terms of V0, when every time you multiply by this matrix? There's a simple thing in linear algebra. This is why you took linear algebra class. If you multiply by a matrix a bunch of times, that's just a matrix power. So V7 is this matrix. It's V6 times this fixed matrix, right? So V6 times this matrix. Let's give this matrix a name. Let's call it P. That's what they call it in the textbook. So it's V6 times P, but V6 is V5 times P. So we have P times P, and then V5 is V4 times P times P times P. So every time you go forward a day, you're multiplying by the matrix P one more time. If you do it on day 7, that's multiplying by P times P times P times P. That's P to the power 7. So you keep this up, you get V0 times P to the power 7. So this is the answer to the 7-day forecast problem. To get from day 0 to day 7, you take the matrix P, you take it to the power 7, and that will automatically keep track of all the possible ways to go in between. All right, so somebody in the chat wrote, how would it be affected if we had a third state? And the nice thing about this example, this is the simplest possible example with only 2 states, but what we've learned works in general. So if you did a more complicated Markov chain, it doesn't matter how many states it has, as long as it has finitely many, you can always do what we just did. And what you'll end up with is that the matrix P will be the number of states by the number of states. So in general, P is a number of states by number of states matrix. P is a number of states by number of states matrix. The entries are given like this. Pij is the probability that xn plus 1 is in state j, given xn is in state I. So you can always make this matrix for any Markov chain, because a Markov chain says to go from state one state on day n to the next state on day n plus 1, it only depends on what happened on day n, right? This is the definition of a Markov chain. So you always have this kind of matrix for every Markov chain. And the update rule works exactly like this. So, and with this matrix, this is called the transition matrix. This is called the transition matrix. The update rule is always that Vn equals, or Vn plus 1 is a Vn times P. So it always works. And this is super duper efficient. It's much more efficient than calculating all the sequences. When you go to do this in a computer, the computer has already got a lot of linear algebra built into it, and things should work out very well. I want to give you an example of this. So I made another question in Mathematize, same thing as before. Let me start this question, and then I'll take a question from Alex. Let me start presenting this. True or false? The most efficient way to calculate a matrix power m to the n is to do n matrix multiplications. M squared, you multiply by m again, m cubed, and so on. So that's a true or false. While you guys are working on that, Alex, go ahead.
So in this case, we had a state space with only two kind of options, but say our state space was like a set of numbers like the integers.
Yeah.
Would it technically be impossible to create an update rule because the dimension is kind of...
Yeah, so in that case, what you really have to think of is you have to sort of think of an infinity by infinity matrix. So everything I'm saying so far works for finite numbers.
Okay.
And your linear algebra class that you took was probably about vector spaces that are finite dimensional, right?
Mm-hmm.
And in this case, we're talking about the vector space, which is like r to the n states. It's n states dimensional.
Oh, okay. Sweet.
Yeah. And of course, you can do linear algebra on infinite dimensional vector spaces. You probably know a couple infinite dimensional vector spaces. One of them is the set of all functions is a vector space, or the set of all polynomials. And so things get slightly more complicated. Of course, you can still do it. And it stops being sort of a matrix is maybe the wrong interpretation, but an operator is still the right interpretation. And so you can do all this stuff on infinite size Markov chains. But for simplicity in this course, we're just going to stick to finite dimensional ones. And that's because the final project, the game, is a finite dimensional.
Okay, thank you so much.
Yeah, it's a great question. The other thing you can do is we've been doing everything in discrete time. So we're saying x0, x1, x2. You can do everything in continuous time. So the time variable is a real number. And that's, again, all of the theory basically works, but you have to do some like tweaks. So we're not going to do that in this class, but it is interesting to do. Yeah, thanks, Rob, for reposting the link. Okay. Yeah, any other questions? Okay, let's see. How are people doing on this true false over here? Okay. 15 people. I guess there's 25 people. So I'll give you guys another minute for the last 10 people to put in an answer. Okay, we're up to 18 people. I'm just going to view the responses and see what you guys think. 19 people think it is false. 3 people think it's true. I guess that's 22. I don't know why it says 20 up here when you add up those numbers. The correct answer is, of course, false. Reveal answer. Display. Okay, here we go. So it's false. And so you guys are right. There are lots of more efficient things that a computer does when you say calculate a matrix power, which is one thing you can do is you can do like a binary search, right? So if you want to do m to the power 8, you can write m to the power 8 as m to the power 4 times m to the power 4. And then you can write m to the power 4 as m squared times m squared times itself. And so your computer can go, you can calculate m, then you can calculate m squared, then you can calculate m to the 4, and then you can calculate m to the 8. So you do 4 operations instead of doing 8 operations, and this scales like the log. So at the very worst case, you're basically doing order log n multiplications, or log base 2n multiplications. That's a simple way. There is an even more sneaky way. So if you were paying attention in linear algebra class, there's actually, if you want to do like m to the power a million, that would be a million multiplications. There's actually a really smart way to do it, where you don't have to multiply anything a million times. So you have to do something else. You have to do some other work. Maybe it's annoying work, but you can avoid doing a million multiplications. Maybe someone can type in the chat if they know, or you can put up your hand and say, what is the sneaky trick? Yeah, someone wrote diagonalization. So if you write an arbitrary matrix M, you got to multiply it a million times. But if it was a diagonal matrix, then you could just do the millionth power of the diagonal entries, which is easy. And if it's diagonalizable, you can write M is, some transformation UD U inverse to the power 1 million. And when you take a diagonal matrix to the power 1 million, you end up with UD U inverse times UD U inverse times UD U inverse times dot 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 UD U inverse. And the beautiful thing is all these U's and U inverses cancel out. So you end up with U d to the power 1 million times U inverse. And so you're doing, if you can diagonalize the matrix, you can do the eigenvalues to the power 1 million, and then you can just multiply by U and U inverse once. So as long as you don't mind doing diagonalization, you can really reduce the work of doing these things. And computers, fortunately for us, do this automatically. So you'll never have to diagonalize a matrix by hand in this course. But knowing like what diagonalization is, that will save you a lot of time. And computers often do this automatically. I'll say one other thing is by looking at the eigenvalues, you can tell what the millionth power is going to do. So for example, if one of the eigenvalues is 0.1 and another eigenvalue is 1, what happens when you take it to the power 1 million? Well, you're going to get lambda 1 to the power 1 million. 0.1 to the power 1 million is basically 0. So you could just say that's approximately 0. And 1 to the power 1 million is still 1. So lambda 2 to the power 1 million is still 1. So basically all of the eigenvalues that have a real part which is bigger than 1, and 1 or more, those will survive sort of in this thing. But all of the ones that have an eigenvalue that is less than 1, those will go down to 0 and sort of not matter. They will matter less and less. This should remind you also of differential equations. So in differential equations, if you have a linear differential equation, you know that the eigenvalues of the system tell you the long-term behavior, whether or not it's attracting towards an equilibrium or if it's exploding away. And it's the same kind of thing with this kind of stuff. So if you look at what are the probabilities doing as you update the Markov chain, the eigenvalues of the transition matrix tell you which directions are shrinking down and going away, and which directions sort of survive for a long time. So to show you this, I have some computer programs here. And so by the way, you can get to all the computer programs. There's like a GitHub page for the course. So you should be able to see these things. So this is the rainy, sunny simulator. And here we have the parameters alpha and beta. And here I made the transition matrix P. Let me do this a little bit slower so we can go over how some of this stuff works. One of the big next examples we're going to do is going to be even more in detail in using the code. And so I'll go over some more details then too, but this is a good time already. So this is all in Google Colab, which is right now, it's not running on my computer. It's running on the computers at Google. And they have things set up very nicely to make it easy for me. So let's see. So far what I've done is I've just imported a bunch of packages that we're going to use. And here I'm basically using this package NumPy to make vectors and matrices. Basically, it does linear algebra on the computer. So to start with, why don't I do just these to start? Okay, it's always a little dangerous doing live coding, but we're going to do it. Okay, so to start with, I set the parameter alpha to 2/3, I set beta to 1/2, and then I made this matrix P. And why don't I print P? So a matrix is an array. So JNP stands for Jack's NumPy. You might have done NumPy before. Jack's NumPy allows you to do all of the linear algebra calculations on the GPU rather than the CPU. And we're going to talk about next class why that's a good speed up. But now I'm going to also print it. So print out this thing, and now it's making this 2x2 matrix. It's exactly the matrix we had over here. This matrix, alpha, 1 minus alpha, beta, 1 minus beta. By the way, you might notice something funny about this matrix. There's a nice coincidence. If you do alpha plus 1 minus alpha, you get 1. Alpha plus 1 minus alpha equals 1. And beta plus 1 minus beta is also 1. So the rows always sum to 1. If you have an honest to goodness Markov chain, the rows always have to sum to 1. And that's because you have to go somewhere in the Markov chain. So the total probability to go somewhere is always 1. The rows of the transition matrix always sum to 1. This is called a stochastic matrix. So rows sum to 1. Sum to 1. That's a stochastic. So if you do the Wikipedia page for stochastic matrix, that's the definition. Okay, so we have this stochastic matrix P, and here I'm doing exactly what I was saying before. with the vectors v0. So v0 is a vector, and it has the probabilities at time 0. Will it print this? I need to say print v0. Okay. So it's a 1, 0, it's a row vector. By the way, you can also print the size of these things to make sure that everything is what you expect. So if you say jnp.size, it will tell us that it's a 2 by 2 matrix, hopefully. Oh no. Yes, I spelled print wrong. Okay. Print. Okay. Size, that's not what I want. 4, that's not what I want. Okay. I want shape. Okay, that's what I want. jnp.shape. Shape. Shape. Give me the shape. 2 by 2. Okay, great. And so similarly, jnp.shape of v0, that should say it's a vector of length 2. And the way it says a vector of length 2, it does 2 comma. That means a vector of length 2. So I have this 2 by 2 matrix. I have this row vector, 2 comma, and I can multiply them together. I'm also going to keep track of the results in a list. Actually, before I do that, why don't I just do some multiplication? Let's do v1, and it's going to be jnp.matmul v0 times p. So this is multiplying one operation. So that's v1. And I want to see the answer. Print v1. Okay. So I'm printing v1. I'm doing the matrix multiplication of v0p. I'm just taking what we did over here, this rule, that vn plus 1 is vn times p, and I am doing it on the computer. Okay. So on the computer, p is this matrix, alpha 1 minus alpha, beta 1 minus beta, and v0, I made it 1, 0, and then I told the computer, please do v1 is v0 times p as matrix multiplication. So if you've done NumPy before and this kind of thing, I think this will be very easy. If you haven't done it before, I'm probably going way too fast. Let's do a little quick poll. So who's seen this kind of stuff before? Seen it before? Hit me up with a yes or a no in Zoom. So yes versus no. And so I might do like a tutorial or something. Okay. Okay, some people haven't seen it at all. Okay, great. It looks like it's about 50-50. So yeah, maybe there'll be a little tutorial on this, on how to do this stuff. So your projects are all going to be written in this kind of language. So you're going to have to learn how to do it. Okay. So yeah, so I made a 2 by 2 matrix by using this array command, and I made a vector using the array command, and now I'm matrix multiplying them together. That's the matmul command. And you can keep going. So you can say v2 is the matrix multiplication of v1 with p, and please print out v2. Okay, and so you can see the probabilities went from 2/3, 1/3, and now it's closer to 60-40. And you can keep doing this. So you could write this out all day. Yeah, and so like I said, these pages are already, I gave them, they're on the GitHub already. I guess I'm making changes to them now, so I can update them as well. So you should be able to see them. So especially if you haven't seen this stuff before, I think it's really good. Go after class or before class and take a look at them, and you can play around with it and write your own stuff and run them. So that is doing them one at a time. Here is doing it with matrix powers, right? So I said that the computer is smart and knows how to do matrix powers better. So to do matrix powers, it's this command, matrix power. And so if you do this multiplication, you can automatically get things like v7. So for example, v7 is going to be the matrix multiplication of starting with v0, and we're going to multiply it by the matrix to the power 7. This is the 7-day forecast problem. All right, I got to print it. Otherwise, we're just going to get the answer, but not what it is. Here we go. Okay, and you can see it's very close to 60-40. So given that it rains today, the probability that it is rainy 7 days from now is 60%, and the probability that it is sunny is close to 40%. And that is assuming we're using these parameters, alpha 2/3 and beta is 1/2. Okay, and I put this together in a loop. So here I made it loop through and just go through and calculate the first 8 days. And so hopefully this will work. I haven't made any bad changes to it. So here it's just going through one by one and calculating the probabilities on any day. So it goes, 100%, 0%, then 2/3, 1/3, then, closer to 60%. And hopefully you can see the pattern with numbers. If you can't see the pattern with numbers, I also plotted it. So I made a plot of the two probabilities. And one of them starts at 100%, is going down to 60%. And one of them starts at 0%, and it's going up to 40%. All right. And you can see that sort of in the long run, it sort of settles down. So this graph, it's just like differential equations. If you took differential equations, when you have differential equations that are linear, they kind of all lead to an equilibrium. And there's an equilibrium solution here, which is the 60%, 40%. So you could ask, what is the equilibrium? So based on our simulations, does the limit as n goes to infinity of p to the power n exist? This would be like the limiting matrix, and you could also ask, what is the limiting probability? The limiting probability would be v infinity is the limit as n goes to infinity of v0 times pn. This is the limiting probability exists. And the answer is yes, 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 this exists. And this is called the stationary distribution. So the stationary distribution of a Markov chain, or the long run distribution, if you start in any situation, rainy or sunny, sort of after a long number of days, you sort of forget where you came from and you just reach this limiting thing. And in our case, it was 60%, 40%. So this is the definition. This is called the stationary or long run probabilities of a Markov chain. Okay, and there are some technical conditions. So I'm going to leave those out. I'm going to say theorem, assume technical conditions. Every Markov chain has one stationary distribution, and the limit as n goes to infinity of Vn is always this stationary distribution. In the textbook, it's called with a pi. So they use the letter pi to represent the stationary distribution. Okay, yeah, so somebody in the chat wrote, if we swap our initial state, what would happen? Let's just do it. And I think this is a good way to illustrate what is this stationary distribution. So where do I want? I want to go here. Okay. So we started in this example. I started with 100% rainy on day 0. Let's do the opposite. Let's make a v0 be the opposite. So v0, instead of being 1, 0, is going to be 0, 1. So what if it starts out sunny? Let's see what happens then. Hopefully this works. Okay, so on day 0, it was 0% rainy, 100% sunny. And then we know on day 1, it's going to be 50-50. That's the rule of the Markov chain. We use the parameter beta, and it was a half here. On day 2, it goes up to 58-42. And then you can see it's approaching the same kind of limit. So it's always going to converge to this steady state of 60%, 40%, no matter where you start from. We could do another example, which is something in between. 50% rainy, 50% sunny on day 0, and you will still converge to the same kind of distribution, 60-40. So you always converge to the stationary distribution. Markov chains kind of have this property. They start somewhere and they sort of like diffuse out until they get really, really close, exponentially close to their stationary distribution. Okay. Any questions or comments about that? That's a good thing to know about Markov chains. Okay, and once again, if you haven't seen this stuff before, if you've never seen, I think it's a really good, you should open this up and play with it and try making your own, like try changing alpha and beta, see what happens. You can try to find the formulas. Like how is 60% 40%? Is there a way to find out what that is in terms of alpha and beta? And I will say, I'll give you a hint, and this kind of idea is going to come up and be an important part in the course. How can you find the stationary distribution v infinity, or what they call in the textbook pi? And you'll notice that if, we have this update rule that vn plus 1 equals vn times p. What if we take the limit as n goes to infinity of both sides? So if we do the limit as n goes to infinity of both sides, on the left-hand side, vn plus 1, hopefully that's converging to v infinity. On the right-hand side, we still have a v infinity, and the matrix P is still there. So the limiting distribution must satisfy the limiting distribution satisfies this. And by using this, you can solve for what it has to be. I think this is in the textbook, and there is a reference. I will get you guys the reference. So in the notes, in the textbook, they compute this. They compute v infinity for the rainy sunny Markov chain. Okay. Great. So that's it for the two state Markov chain. I think we've understood everything there is to understand about it. So you can go back and forth between these two states. We know how to compute the probabilities. It's matrix multiplication. If you like linear algebra and are tuned into linear algebra, it's going to be very easy for you to see how things are working. You can calculate things like this long-term thing. It's also related to eigenvalues and eigenvectors. If you look at this equation for long enough, I think you will also realize it's got something to do with eigenvectors and eigenvalues. And that's it for the two-state. And the same idea works for n states. And that's, like if you understand this idea of updating with the matrix, you understand and most of this kind of like basics of Markov chains. There's a couple things you still need to learn about Markov chains. And the next question I have for you guys in Mathematize, we'll end with this one today and we'll take it up tomorrow. This is example 4.4 in the textbook. Let me make it full screen. Very similar idea. We want to do rainy or sunny. There's two types of weather that can happen on any day, but the rules are different. So there are different rules now. And the rule now depends on the weather on the past 2 days. So if it rained for the past 2 days, then it rains tomorrow with probability 0.7. If it rains today, but not yesterday, then it rains with probability 0.5. If it rained yesterday, but not today, then it rains with probability 0.4 tomorrow. And finally, if it hasn't rained for the past 2 days, then it rains tomorrow with probability 0.2. And the question is it a Markov chain? Is it a Markov chain? So you can say, yes, it's a Markov chain. No, it's not a Markov chain, or it depends. And I'll let you guys answer this one, and we'll take up the answers next time. So put in your answer now, what you think it is. It's okay to be wrong. Just take a guess at it. Okay, so I'll reveal the answers when we get to like what has it been? It's been, oh, here we eventually got to 21. Okay, when we get to like 15 or 16 or something, I'll reveal, and we'll see what people said, and then we can go home. I guess you already are at home, probably. Okay, let's see what people are saying. Some people say yes, it's a Markov chain. Some people say it depends. Some people say no, it's not a Markov chain. So it looks like the class is completely split on whether or not it's a Markov chain. So I think that means that you guys got to think about it. Think about this example. I guess, you can always cheat and read the actual textbook and see what the deal is. And we're going to take this up next time. So if someone tells you a Markov chain, everything is linear algebra. But if somebody gives you a problem like this, it's not clear, is it a Markov chain or not? What's going on? That is part of the difficulty. Okay, so it's 12:20. I'll officially stop here. I'll stick around for questions if people have them. Next class, we're going to do even more programming. So I will I'll go over some of it with you for people who haven't seen it. But it's a good idea to play around with the week 1A file. I guess I can post this version as well, but you should be able to play around with it and see it on the course GitHub page. Okay. Yeah, any questions or comments? Feel free to put up your hand, or I think you can just start talking. Yeah. Matt, go ahead.
I got a quick question.
Yeah.
I was just wondering because I was going to ask it earlier, but I feel like it would have attracted a bit or like tangented the lecture a bit. When you talked about the cyclicness of when you talked about like the limits of a Markov chain, right?
Yeah.
Can you have the limit be like a cyclic sort of behavior where it goes back and forth between like one or two states?
Yeah, you can. So I said in my thing that there are some technical conditions, and the technical conditions are basically that you don't have these kind of deterministic cycles. So the thing that can happen, and I think what you're talking about, is you can imagine a Markov chain that has 3 states, and it goes to the next state with 100% probability. So it kind of goes like this.
Yeah, I see.
And if you do that, of course, there's no limit, because if you start, you start here, then the next time you're going to be down there and over one and up one, and you're just going to go around. So there's no limit. But as long as you make one of these, if you make one of these 99%, and then it has like a 1% chance to go the other way, already it's fine. So now just that 1% chance is going to ruin the like perfectly cyclical nature, and it will have a limit. So
Okay,
as
cool.
long as you don't have these like silly like deterministic things that are really like not random, it will have a limit. The other thing you can have is it can be not connected. Like you could have 2 states over here that are like going back and forth, and then 2 states over here that are going back and forth. And then of course there's no unique limit anymore, because like you have some limit for these 2 guys and you have some limit for these 2 guys, and they don't communicate. So that the technical conditions say basically it's all one Markov chain. It's not secretly 2 Markov chains that are like masquerading as one Markov chain, and you don't have any stupid like cycles with 100% probability.
I see. Okay, makes a lot of sense.
Yeah, and if you want, you can read the technical things in the textbook. So I think section 4.4 has all of these technical details.
Okay, thanks.
Yeah. Yeah. Anyone else? Yeah, Alex, go ahead.
So just in terms of using the Jupyter notebooks,
Yeah.
is there like any documentation, like what packages we should probably be comfortable in using throughout?
Yeah. So we're gonna do everything in NumPy, like which is all this like linear algebra stuff, like vectors and stuff like that.
Mm-hmm.
And I'm specifically going to try to teach you guys how to use this one called JAX. And JAX is exactly the same as NumPy, except it runs on the GPU. And we'll see next class that that's a lot faster for the kinds of things we want to do in this class. So yeah, you don't like, if you've done NumPy before, this is exactly the same. If you've never done NumPy before, I think you'll pick it up as we go, and I'll spend some time giving you guys some pointers. But it really is just like linear algebra on the computer.
Mm-hmm.
Yeah. Have you done this kind of stuff before in any of your classes, or not really?
I'll be honest, I took a course in first year called IPS, and we did have to use NumPy in it, but I have no recollection of ever using it.
Yeah. I think it'll come back to you as we go, because it's if you've done a little bit of Python before, all the Python-y things that you need to know, like for loops and stuff, and like definition, those are the Python-y things. And then other than that, there's the NumPy things, which are things like make an array, do a matrix multiplication. So if you've taken linear algebra and you know like a little bit of Python, it's not too hard to put it all together. So yeah, I'm hoping that won't be like a big obstacle, although if you haven't seen it before, of course it will be an obstacle that you'll have to get over.
Okay, I just had a second question, and it's about the notebooks that we're going to be submitting for our projects.
Yeah.
How meticulous do you want us to be in documenting our code?
Yeah, so I think I'm gonna release like a more specific rubric, and I might like consult with you guys on what you think should be there, because part of the grade is like the peer review. So it's like, what do you want to be, what should be in the notebooks? And there definitely are going to be like math things like this, where you explain math as you go. And then inside the actual coding, I think we're going to do something like have a contract on every function you write that tells you what are the inputs and outputs, to make sure that people can understand like what it's doing. And then you're going to have small comments here and there just to explain what things are. And so there'll be some kind of like one of the items on the rubric will be like, is the code like well explained? Does every function have this thing and stuff like that? So yeah, it'll be like a specific instruction on what you have to write.
Okay, sweet. Thank you.
Okay, and I lost my headphones, so if you said something, I missed it. Go ahead.
Oh, I just said thank you.
Did I? Oh yeah. Okay. Great. Yeah. Does that? I don't know if that answers your question. I'm trying to put this together now. I was kind of waiting until I was thinking that probably a bunch of people would drop the course after the first day, but it looks like that hasn't happened yet. So we'll see at the end of the week, I guess, how many people are actually in the course, and I'm going to try to make everything like that so it's not too much work for you guys to read everybody's and that kind of thing in terms of the peer review and everything like that. Okay. Anybody else for questions?
Just one comment about the notebook.
Yeah.
I'll say that maybe the best idea is if you have some like sort of example notebook that we could use as a basis for what you're expecting is probably the best way to.
Right. And so
something.
the one thing you can look at is the final project is to play this game, but you only have to write the AI for the game. I have already written like the rules for the game, which is on the GitHub. And that has exactly, I think, the kind of level I'm expecting with these contracts like this and like the kinds of comments. So you can check that out. It's already on the course GitHub.
Then I will use that. Perfect. Thanks.
Yeah. Okay. Yeah. Thanks, Matt, for the. I believe your name was Matt. It says MK. So
yeah, it's Matt. It's just that
okay.
For some reason Zoom truncates the name, so MK is what
I believe you can rename it.
Okay, then I'll look into that.
But it's up to you. Yeah, it's whatever you want. It's not a big deal. Yeah. Okay. All right. Anybody else for questions? Let me stop recording actually, in case you want to ask a question that's not recorded.